All right, we can get started. Thank you all for joining us today, and welcome to the Data Science Seminar Series from the University of Washington eScience Institute. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot Nation. I'm excited to have our speaker here today. This is the first talk sponsored by an emerging special interest group on campus that focuses on the environmental impacts of data science. If you would like to learn more about the group, sign up to get informed and notified of events or share your own experiences. I just dropped a link into chat to learn more about that. So joining us today is Emma Strubell. Did I pronounce your name correctly, Emma?
It's Strubell, but it's okay.
Strubell. Thank you. Is Emma Strubell. Dr. Strubell is an assistant professor at the Language Technologies Institute in the School of Computer Science at Carnegie Mellon University and a visiting scientist at the Allen Institute for Artificial Intelligence. Previously, she held research scientist roles at Google and FAIR after earning her doctoral degree in 2019 from the University of Massachusetts Amherst. Her research lies at the intersection of natural language processing and machine learning with a focus on green, computationally efficient AI. Her work has been recognized with multiple Best Paper awards, and you may have seen it cited in news outlets such as the New York Times. We are looking forward to Dr. Strubell's talk, and I would like to invite her now to share with us some highlights from her research. The title of her talk today, Environmental Impacts of Large Language Models, What, Why, and How. And as a reminder, please use the Q&A button on the bottom of your screen to ask questions. Thank you.
All right, thanks for the lovely introduction, and thanks for inviting me. I'm excited to be here. So today I want to talk a bit about like some of my work and others' work as well in the direction of large language models and potential impact on the climate and their energy use. So a bit about like why you should care, what we can do about it, and how. So yeah, so I guess given the focus of this like seminar series and the special interest group, I'm sure this slide isn't necessary. So I'll skip through a little bit and just focus on, I think, a lot of the media coverage and sort of like general discussion around the relationship between AI and the environment and large language models in the environment has been really focused on the fact that, computers use energy and, many of the ways in which we produce energy create a lot of carbon emissions and greenhouse gas emissions, which is contributing to the current climate crisis. And something that I'd like to emphasize in this talk is that I actually think that AI has great potential to potentially positively or negatively impact the climate. And it's sort of us. We have the power to, shape the ways both the models that we devise and the ways that AI is used. And I'll talk about this a bit more in this talk in order to sort of either align AI and align this really powerful technology, with sort of potentially positive or negative impacts on the climate. And I think we're going to need to use AI in the same way that we're going to need to use many different sort of state-of-the-art transformational technologies in order to affect the sort of wide sweeping, cross-cutting changes in our world in order to, try to limit global warming to a safe level. Okay. So of course, machine learning models are growing. They're growing very rapidly. They're continuing to grow. I keep having to sort of like update this slide, and it's like it's perpetually very out of date. So here I'm sort of showing over time the size in terms of number of parameters, which is sort of like a proxy for the sort of computational efficiency of the model of a bunch of large language models from starting in 2018 until 2022. And you can see in this sort of like most recent-ish plot that I have here, we've switched to a log scale on the x-axis because they're growing so quickly and so large. And we don't really know how large ChatGPT is, but it's probably somewhere in the scale. It's somewhere in the scale. And so you can see that machine learning models are growing very quickly in size. So these are all language models. This is a trend across sort of all of AI, not just in natural language. And so here's a similar chart for sort of more general sort of artificial intelligence models for game playing, like playing the game of Go, and we can see the same trend. And then this is a plot from a recent-ish paper on sort of scaling properties of language models, and this is specifically for scaling image transformers. This is in the area of computer vision. And so sort of noticing this trend and wanting to actually sort of quantify it and bring it to the attention of initially my NLP research colleagues, in 2019 with collaborators, we wrote this paper where we were trying to estimate the carbon footprint of a bunch of popular, successful and seemingly large at the time NLP models. And so what we found in this paper is that the energy consumption of these models is growing in step with their computational requirements, and potentially their carbon footprint as well. So here in this chart, I've listed the estimated carbon footprint in pounds of a number of common benchmarks, such as air travel for one passenger between New York City and San Francisco, and the carbon emissions for the average American for 1 year. And we found, for example, that the GPU time required for me to tune and like me at the time, just a graduate student, to tune and develop a model that I presented at a research conference in 2018, like could have effectively doubled my personal carbon emissions that I would have otherwise have produced that year. Luckily, we actually used sort of like a green supercomputing center, run on renewable energy, so it didn't actually double my carbon footprint, so that's nice. And sort of more notably, training a machine translation model using neural architecture search, if done using GPUs, could produce more than 2 times as much carbon as a car during its lifetime, including all of its fuel consumption. And so, these numbers are now like a bit old. The models that we were looking at are actually a lot smaller than the models that people are training and using now in this area. So more recently, we published a paper in Fact last year, and this was a collaboration with folks at AIQ and folks at Microsoft Azure, where we're sort of like, we're updating these numbers, as well as sort of proposing some potential ways from the cloud compute perspective of giving like cloud users some more control over the potential carbon emissions of their models. I'm not going to talk about that in detail now, but I'm happy to answer questions later. So here are some updated numbers with some much larger models that are more recent. And so here, again, we found that the marginal emissions, so this is like the sort of additional carbon emissions that are due to training this model versus not training this model, due to training a 6 billion parameter transformer language model. So this is, the type of model that these large language models are. Was comparable to the energy required to power the average US home for 1 year. And I'd also actually like to note that we didn't want to rerun any experiments and use additional carbon in order to write this paper to the extent possible. And so actually these numbers are for a model that was sort of only 13% trained. So it wasn't fully converged, but the checkpoint we had was sort of like 13% of the way of like what the full model would have been trained. And so the full training would have required actually a lot more energy. And potentially therefore emissions. And these are the actual emissions from this model training happening at Microsoft, like in their actual data centers. So so that's interesting. And that being said, to my surprise, this paper actually got a huge amount of press coverage and a ton of interest. Well beyond the sort of like little research community that I had sort of intended to write it for. And it's still, I'm getting a bunch of media inquiries now about like, what are the carbon emissions of ChatGPT? And while I'm glad that we, helped bring attention to the potential environmental impact of these models, and I think this work, along with other work sort of that was concurrent with ours, has helped to spur a ton of interest in the area of efficient machine learning. Unfortunately, I think there's been a lot of misunderstanding and hyperbole around the actual implications of our work. So I want to directly answer the question, is large machine learning model training sort of like single-handedly destroying the planet? I would say probably not, at least probably not due to the greenhouse gas emissions from their operational embodied use, energy use. And I'll explain in a minute exactly what I mean by that. Right now, I will explain this asterisk, which is that people aren't really doing a ton of the accounting with respect to how much energy these models are using, in particular when it comes to inference. So recently there have been some more numbers that are published, and again, I'll talk about these a bit in these slides. But like, for example, it would be really interesting to know sort of what the marginal emissions or marginal energy use impact is of, for example, like a ChatGPT-like model being incorporated into Bing search versus, the old Bing search. How much more energy is that using per query? I don't know. People aren't really reporting that. And so it's hard to know actually what the sort of marginal emissions are due to AI. And so by the operational and embodied energy use, so operational use is the energy use due to like actually sort of running the model, or like the energy required to in the whole machine learning model life cycle. So to train and develop and run the model. And then embodied energy use is, or embodied emissions are the emissions due to actually like the hardware supply chain. So there's a lot of emissions involved in making hardware. And I want to quickly put a shout out to this paper that I really like, where they specifically were sort of like looking at the emissions due to the hardware supply chain, which is surprisingly important, especially as increasingly our data centers are being powered by renewable energy, or at least being sort of offset by carbon credits. Increasingly, we need to think about like our hardware life cycles, particularly as we increasingly depend on more and more specialized hardware, which actually requires more and more specialized sort of like processes. So I want to highlight this sort of quote directly from the paper, which I think is a really interesting analysis they did. And so they basically compared like, what is the carbon footprint of the hardware manufacturing of a Google Pixel 3 smartphone, and how does that compare to like running inference in a machine learning model? So they compared that footprint to the carbon footprint of running ImageNet, like inference in like a ResNet architecture for doing image classification on ImageNet. And it was equivalent to like continuously running inference in that model for 3 years, which is actually beyond the average lifetime of a smartphone. And so when you're thinking about like where to focus energy and where to focus concerns in terms of like the carbon footprint of sort of our field and of like technology generally, the hardware makes a big difference, because the footprint of the hardware itself is actually much larger than if that phone had been constantly running like a machine learning model throughout its lifetime. Yes, and then the other thing I would like to note here is the hardware supply chain also has like a lot of other sort of environmental and social impacts beyond just the energy use and the carbon emissions. One of them is water. So manufacturing hardware actually requires like a huge amount of water, and hardware is not always manufactured in places where water is readily available. So for example, as a result of the recent CHIPS Act in the US, which is like encouraging, building more chip manufacturing plants in the US, one of the big new plants that's being opened is, I believe, in Arizona, which is a place that does not have a ton of water, and in fact, where like water rights are sort of under dispute and the water is drying up. Yeah, and so by some estimates, the average semiconductor factory uses as much water in a year as a town of like 50,000 people. That's like approximately a number that I was able to find. And then another resource that is sort of scarce and potentially problematic that is really important for today's hardware, and again, especially today's sort of specialized hardware like GPUs, is rare earth minerals. And this is a problem both because they're actually sort of like a scarce and limited resource, and we don't have an infinite amount of rare earth minerals, but also the mining practices that go into obtaining those minerals from the earth can sometimes not be ethical and can be harmful to the people who are mining those minerals and people who live near places where those minerals are being mined, as well as just sort of being harmful to the environment. So this is an image from an article in the New York Times about illegal mining in the rainforest in Brazil, and it's sort of like indicating this aerial view of sort of indigenous homes in the rainforest, and they're sort of juxtaposed against these illegal mining pits that are very toxic for the environment and harmful to the people who are living there. And those supply chains are not very well monitored. So yeah, so sorry, that's my that's my side note on the hardware supply chain, which I don't really work on, but I think is interesting and something we should think about. You know, even if you're not working on sort of hardware yourself, I think in terms of data science, there are really interesting problems in how we can, well, there's many interesting problems. I'll talk about some of them later in this talk. Things I won't talk about in this talk because I don't really work on them, but maybe you could be interested to work on them, would be, you know, how can we better optimize our data centers? How can we better keep hardware around longer? So the average time that hardware is replaced in data centers is like every 2 to 3 years. But do we need to do that? Or can we sort of like figure out ways of using that older hardware and sort of getting more use out of that manufacturing? Yeah, okay. So jumping back. Yeah, so now I want to go into, yeah, okay, so probably not. Oh, one thing that I meant to mention earlier is, again, it's hard to get these estimates, but if you're thinking about like sort of how much of the global energy use, for example, is actually due to like AI and machine learning, one estimate that is out there is that data centers are responsible for a little under 1% of like global electricity use. And so probably a relatively small subset of that is actually being used for AI and machine learning. Like later in this talk, I'll talk a little bit about you know, some other places where research can potentially have impact, but that are actually making up like a much larger portion of the greenhouse gas emissions in the world. Yeah, so now I want to quickly explain a bit more about operational and embodied energy use, and sort of take a look at the bigger picture of emissions and interactions between AI and the environment. That might be, you know, there's a positive and a negative. So more exciting to tackle using machine learning and data science, or conversely more likely to sort of lead to the end of the world as we know it. Yeah, okay, so this is sort of like a figure overview of some of what I was just saying in terms of like sort of what statistics do we actually have on sort of how much of global greenhouse gas emissions are coming from like AI and machine learning, and sort of how to think about that. So we have this big gray bar that's sort of like all global greenhouse gas emissions. This purple part at the very top represents ICT, which is sort of like information technology sector of the world. And so of that, we don't really know what this number is, but like some portion that's probably relatively small is AI related. And then of AI related emissions, we can sort of divide it down into operational and embodied emissions, which I described before. And so increasingly in recent years, companies are starting to report some of these numbers. So that's really interesting. So at Google, for example, they reported that machine learning workloads make up 10 to 15% of their total energy consumption. And that was pretty consistent across the 3 years that they measured it in this study. So in 2020, that was 1.5 to 2 terawatt hours of energy being used by Google to power machine learning workloads. So that includes like training, inference, et cetera. And so I mentioned training and inference. So when we think about sort of what are the carbon emissions of machine learning, one of the important things that I think I did a bad job of communicating with the press early on, but I'm sure, again, people here probably know what I'm talking about, but it's that sort of different phases of the machine learning life cycle have very different sort of like use patterns, as well as emissions. And so here I'm depicting the different phases of the machine learning lifecycle. So you have training, which is training a single model, development, which typically involves training a bunch of different model variants to figure out the one that's going to work the best for your application. And then there's inference, which is actually using one of these trained models to infer, for example, a label on your data. And so a single inference typically requires much less energy than training, which requires running inference a bunch of times, as well as learning, computing errors, and backpropagating. And then development is much more energy intensive. In our previous work, we were looking at the carbon emissions due to training and to some extent development, not inference. On the other hand, inferences are run much more frequently than training runs or development runs. So while a lot of focus so far, I sort of mentioned this earlier, a lot of focus so far has been on the emissions, the surprisingly large emissions due to these actually relatively rare events of training and developing very large models. It's sort of not so clear how these things actually trade off, because even though a single inference requires a small amount of energy, how many inferences are actually being run in the case of a model deployed in the world, like Google search or Bing search or Google Translate or something? I don't know if I have the statistic in front of me, but like some number of years ago, it was reported that Google Translate translates like 3 billion tokens per day or something. So that represents like a lot of inferences in one of these models. And so from that same paper that I sort of referenced before, it's at the bottom of this slide, from Google, they did some of this accounting, and they estimated that about 3/5, so we said it was like 1.5 to 2 terawatt hours a year for machine learning. They estimate that about 3/5 of that is actually for inference, and 2/5 of that is for training. So even though inference is much cheaper, it adds up, because like running these inferences is a large part of their business model, right? Because you're also running machine learning inferences in order to serve ads, on Instagram, on TikTok, as well as to do a search query. Meta has also reported some similar numbers. Hopefully people will find this interesting. I think it's interesting, so that's what you get to hear about. And this is from that paper. And so they're also breaking down their energy use into sort of experimentation, which is like the development phase, model training, so that's like the retraining of models that are in deployment, and inference. And you can see it's like a pretty similar picture. It's maybe like 2/3 of the energy that they're using is for inference, so fueling the ads in your news feed or your Instagram feed or whatever. And then the other third is actually sort of developing models and then and training them. Another takeaway that I thought was very interesting from this Facebook paper is that, Meta, is indicated in this bottom bar that you can see, that's sort of like yellow and black. And so it's labeled RM1. And so this is one of their ads models. And so again, they're sort of breaking down the energy use of that ads model into data, training, and deployment. And the portion devoted to just like holding and dealing with data for that model, like consuming and putting data somewhere, holding data somewhere, is this yellow part. And it's super high. It's like 32% or something of the entire energy use for having that ads model is just holding data. And so again, it's like as data grows big, so too does its potential carbon footprint, and certainly the energy required to just like manage all that data that's being generated by users at Meta, and has to be processed into some kind of useful form. So I thought that was really interesting as well. Yeah, and so yeah, I need to put this plot in here. So there's this sort of interesting, I alluded to this a little bit before, but there's this interesting thing where I was mentioning that the from this Google paper, they report that the so they're basically their energy use due to machine learning was quite consistent year to year. So the proportion of their total energy use from year to year was quite consistent. But they also noted that their energy use grows pretty substantially every year. And if you plot how the energy use of not just Google, but sort of like all of these large tech companies year to year, that's the thing that they tend to report. They maybe have to report it, I don't know. And you plot it like alongside their revenue year to year, you can actually see that those things are growing right in sync. So there's sort of this interesting question of the extent to which large tech companies actually sort of require energy and potentially carbon emissions if they're using non-renewable energy, which they are for now, in order to make revenue, which they're required to do in our capitalist economic system. Yeah, okay. Okay, so now we kind of drilled down deep now into sort of where carbon emissions, or at least where energy use is coming from in the world of machine learning. Now I want to step back a bit and think about the big picture a little bit more that I alluded to earlier. So all that stuff I was just talking about, it's actually like a relatively small piece of how AI interacts with our world and interacts and has the potential to have a positive or negative impact on our climate. And so that's what this figure is sort of trying to depict. And this is from, so we sort of formalized this framework. This where all these figures are coming from is a paper from last year that I worked on with collaborators that was published in Nature Climate Change on, yeah, basically this framework for how sort of policymakers and climate people can think about the sort of relatively complex interactions between AI and climate change mitigation. And so all the stuff we've been discussing so far are what's indicated as compute-related impacts here. So those operational embodied impacts due to developing and using AI. And so in this chart, you'll notice there's actually a lot of other potential impacts. And the way that this chart is organized is that as we move further away from the center of the circle, we have sort of both increasing uncertainty. So it's increasingly difficult to estimate or understand the impacts and the direction of those impacts, whether positive or negative. But also the potential scope increases drastically. So there is much larger potential to have a positive or negative impact. And so what are these sort of other concentric circles? So one is they have to do with the applications of our technology, and then the sort of downstream like rebound effects and downstream effects of those applications being deployed in the world. So immediate examples of immediate application impacts are thinking about, whether our technology is being used for sort of to enable smart buildings so that buildings can be more efficient in their, HVAC, their heating and cooling, and like whether the lights are on, or are we using those technologies to enable like more drilling for fossil fuels, which allows for more burning of fossil fuels and reliance of fossil fuels. So those are two different applications of machine learning technology that can have very different impacts on the environment. And in this paper, we sort of argue that, again, the numbers are hard to get in a large scale way, but we argue that actually the potential impact for these applications is much more substantial than the potential impact of just building and using the models. And then an example of sort of system level impacts would be, depending on, for example, how self-driving car technology is deployed, that can cause so many sort of like downstream effects. So if self-driving car technology leads to more individual cars on the road, that's probably not going to have a great impact on the environment, versus if self-driving technology is used to massively increase public transit, that actually could have a great impact on the environment. And so those things all kind of interact in a really complex way, but that has the potential to like completely reshape our economy, and our relationship with the climate. So this is just sort of like an overview of some examples and thinking about how certain specific applications in machine learning can have a positive or negative impact on the environment through sort of different mechanisms. I'm probably already going like way too slow, so I'm not going to talk about this in detail now, but it's in these slides, and then it's also in this paper that's referenced at the bottom of the slides. But this is sort of summarizing a little bit of what I just said. Okay. Okay. So a lot of what I've just said has sort of maybe led to the conclusion that like we actually just shouldn't really care about the energy efficiency that much of machine learning models. And yet it's still a thing that I like work on and care about and think is really interesting. So given all of the things that I just said, should we still be concerned about the unprecedented computational requirements of large models? I say yes. So there's many sort of practical reasons that it would be nice for the state-of-the-art models to not have to be like enormous and run on in a data center. So some practical examples are we would like to be able to run machine learning on device, ideally in places where we might not have internet. So this is like a little locobot, like a little autonomous robot that we may want to run in a situation where there's no Wi-Fi and no 4G. This is sort of just like an infographic, kind of emphasizing that the devices are the hardware that we often think about. And when I say we, I mean, at least researchers in machine learning and NLP, we're always focusing on sort of like servers of some kind, or like maybe a laptop or something. But actually this represents like a relatively very small proportion of like all of the devices in the world. And so it'd be represented by this like less than 100 million servers dot on the left. Whereas actually, most devices are going to be like embedded devices, IoT devices, and less so, but at least a lot more in servers, phones. And so there's sort of this really drastic mismatch between the technology that we're targeting, at least in our research, and like the technology where machine learning actually could be potentially really beneficial, or there's a huge opportunity to deploy machine learning in those places, but we can't do that right now. And I think not enough people are working on that. So the other issue that I also think is really important that motivates, I think, working on making models smaller or making models more energy efficient is an ethical issue of equity of access. So as our models become increasingly large and computationally hungry, they're also more financially expensive to use and develop and shape uses of this technology. So what that means is that as our models sort of become more powerful and more promising and larger, like increasingly fewer people or organizations actually have access to that technology because it costs money. And that's a barrier of access. So from that old 2019 paper, we have this big table, and there's this whole column in the table actually devoted to cost that sort of no one really talked about as much as like the carbon emissions column. But the cost of building these systems is quite high. And so here, I'm not going to talk about this in detail, but you can notice that one of the lines is like $1 to $3 million to do some model development. And so these numbers are if you were using cloud compute resources. The lower bound is sort of like cheaper cloud compute, like really cheap cloud compute. Upper bound is like nicer cloud compute as of 2019 on Google Cloud. Yeah, and then so I included here, again, I'm not sure, I haven't recalculated this. I don't know if there's information available to recalculate this for ChatGPT, but at least for GPT-3, the estimate for how much that would have cost is about 4.6 million to train that model. Yeah, and I think, yeah, again, I haven't done the full math, but training Bloom, which is like the open source equivalent of GPT-3, required more than 1 million GPU hours. And yeah, we don't have 1 million. I think it's similar to GPT-3. So developing Bloom also maybe 4.6 million. Yeah, and so now I have some slides on why this is important. I think I don't necessarily have time to go through this slide in complete detail, but the point is that I would like to sort of convince you why it matters, like why it should matter for a wide variety of people to be able to develop and use and work on these models and think about how these models are applied. I guess one is like, maybe if the climate crisis is, more directly impacting you, you'll be more motivated to figure out how we can use these models to combat the climate crisis than, maybe me, because I'm, going to be relatively okay. This is another example that I really like, and then I think I won't talk about the other examples in this slide. This is a paper from 2017, working on the problem of language identification. So this is like a really common task. It's often like the first step in many NLP pipelines. So if you're using some kind of social media and it asks if you want to translate like a post, the way that it figures out what the language is of the post in order to translate it is language identification. And so, this task was considered solved for most languages, certainly solved for identifying English with like just a few tokens many, many years ago, and many years before this paper was published. But that's because they were considering only sort of maybe American English or British English. But there's actually like many more Englishes that are spoken in the world. And so what this chart is showing is the y-axis is sort of performance of a out-of-the-box language identification model. Maybe a couple out-of-the-box language identification models on Englishes, and on the x-axis are these different Englishes are ordered according to the Human Development Index of the origin country of that English. Yeah. And so this is like sort of a proxy for how much access to resources, financial monetary resources, people who speak these Englishes have. And there's a sort of pretty clear correlation. So the out-of-the-box model is the blue line here. There's this quite clear correlation between the performance of an out-of-the-box model on a given English and the wealth of the country or the places where that English is spoken. And so in this paper, the other lines are like improvements upon that. So they proposed approaches for improving that, basically, which is great. But the point that I'm trying to make here is that maybe this wouldn't have happened if more people who speak those Englishes were like involved in the NLP community. And I think it's becoming there's this interesting dichotomy where it's sort of becoming increasingly easy to get sort of involved in machine learning because of the widespread development of packages and tools and things like Hugging Face and YouTube videos on like how to do machine learning and how language models work and things like that. But I think as soon as you actually want to try to train a model and do something interesting, or even just use like the ChatGPT API, things can get really expensive really quickly. And I think that's a problem. And we need to make models smaller and more open. Okay, I want to move on so I actually have a chance to talk about some actual like research my students have been doing in this area. So I'll skip the rest of the slide, but hopefully the slides are shared, or at least I guess you can follow up on the recording. If not, because I have sort of like links to all these interesting papers if you're interested in thinking about these things. And then I will skip this slide as well. Okay, so let me think, how much time do I have? Okay. Actually, can someone tell me, or am I gonna be, when do I need to be done? Like, when should I?
5:30 would be the latest, I think, but we won't have time for questions. So
Yeah. Thank you. Sorry. Okay. So now I want to talk a bit about like what do we do, or like what do I do like in this area to at least to try to make you know, to make these powerful machine learning models more efficient. So these are a bunch of things that you can work on. I'm not going to talk about the compute infrastructure aspect. I mentioned this earlier. There's a lot of cool things to work on there in terms of like data center efficiency and, you know, innovating hardware and figuring out low carbon electricity. I don't work on that, so I'm not going to talk about that in this talk any more than I already have. What I am going to talk about is one method in terms of sort of model development to make models require less energy, which is how can we make these large models smaller or avoid them altogether if they're not needed without sacrificing accuracy. So how can we make these models smaller without sacrificing their performance? So one really common solution to this is model compression. And so the premise is that these really large models are actually really over-parameterized. So you don't actually need all of these parameters for the models to still perform sort of just as well on many of the end tasks that you want them to perform. So you know, your first question, if you're not so steeped in this area, maybe okay, then why don't we just make why don't we just train smaller models? Why do we make them so over-parameterized? And that's like a very interesting question that's worth exploring. It seems to help in optimization. And so if you're interested in that work, you can explore, for example, the lottery ticket hypothesis, which I've linked to here. But basically, it's a lot easier to train large models. They fit more easily and better to our data. So typically in the area of model compression, you're taking one of these large models, and then you're figuring out how to take that large model and then make it smaller. There's less work on how can we sort of train a smaller model from scratch, although it's also interesting. Yeah, and if you're not familiar, I'll briefly mention sort of what the lottery ticket hypothesis is. So it's a hypothesis for why larger models are easier to optimize. And the idea is basically that the more parameters and connections between those parameters that you have, the more likely you are to start with a lucky initialization of, you know, weights, of weights basically in your model and connectivity in your model, which then is sort of good and easy to learn, or it is then easy to sort of train using, you know, stochastic optimization, that random initialization of weights to do whatever your end task is. But then, you know, sort of once we randomly find that nice lottery ticket, then we can sort of like compress, figure out ways of like only using that ticket in a way that's efficient on our hardware. So I'll sort of quickly go through what do I mean when I say model compression. So knowledge distillation, so like Distilbert, is an example of model compression. And so the idea there is that you want to train a smaller model to have the same activations as a larger model. Many of these are sort of older ideas, but you know, we've made them work more recently as well. Another popular approach to model compression, which is a bit more hardware dependent, is quantization. So the idea there is to use many fewer bits to represent each model parameter, right? So typically, you know, each parameter in our model is by default like a floating point number, so 32 bits typically. And so quantization is like, okay, well, can we get away with 16 bits? Yes, usually can, but can we get away with like 8 bits, 4 bits, 2 bits per parameter? And then how do we arrange that? Are there certain parts of the model where it makes more sense to have fewer bits to represent each parameter? And how do we effectively learn the sort of scaling function or the translation from the higher resolution to lower resolution space. And then the other big area in model compression is pruning or inducing sparsity in models. So the idea here is to just remove unnecessary model parameters. So the most common way to do this is with magnitude pruning, which is basically you have your trained model, and then you perform this iterative process where you're sort of just iteratively removing the lowest magnitude parameters because those are the ones that are contributing the least to model predictions. And this works really well. I mean, you can prune like 95% of like a ResNet model for image classification and get the same accuracy. So the question that we asked in our research, and I'm going to talk about a recent paper from students in my group, is, can we improve compression by learning simpler functions in the first place? So when we're initially sort of training this model that we know we're going to want to compress, is there a way that we can train it to be more compressible in the first place? And so the answer is yes. And so this is work with my students, Clara Na and Sanka, aka SVM, awesome initials. Maybe it would have been more awesome like 20 years ago, but I think it's still cool. Yes, okay. And so the idea is to train flat and then compress. And so what do I mean by flat? So I mean, we want to find model parameters that are in a flat minima in the loss landscape. And so again, this is actually a really old idea. There's a paper called just flat minima from 1996 from like the first neural network era. And so there they define flat minima as large connected regions in weight space where error remains approximately constant. So the idea is that you can sort of perturb your parameters relatively to a relatively large extent, and it doesn't change your loss with respect to your end task and your loss function. And so that looks flat. So this are some visualizations from another paper on sort of intuitively what a real sharp minima versus a flat minima might look like if you plot the sort of loss contours. And so I initially sort of made this overclaim that we really don't like prove in our paper, but it's sort of the intuition that's there, which is that flat minima correspond with simpler solutions, lower complexity, high generalization solutions. So this is kind of a nice approach because there is like a growing body of work, both sort of theoretical and more empirical evidence, connecting flat minima, models that are in flat, or parameters that are in flat minima with these sort of like simpler and much more generalizable models. And then so the idea is that a simpler model should require fewer parameters to represent it. Another intuition for why this should work is, again, if we define flat minima as models in flat minima as ones where we can sort of perturb the parameters and not see much change in the loss. Well, if you think of pruning or quantizing the parameters as a perturbation, then hopefully these models in flat minima will be more robust to the perturbations that are due to model compression and therefore maintain their accuracy sort of better as you remove parameters. Okay, so how do we train flat? How do we learn models that are in flat minima? There's a few different ways. We experimented with a couple different ways in the paper. The way that works the best is to just directly optimize for flat minima. So we used sharpness aware minimization. This is an existing approach. And so you're basically, you're optimizing sort of two objectives at the same time. And so you want to move sort of both in the direction according to your sort of normal end task loss function. And then you also want to move in the direction that is going to, so you're also optimizing for parameters that are going to be in a neighborhood of uniformly low loss parameters. So you basically, so you're using like a minimax objective to compute an update that minimizes the loss with respect to sort of like a bounded neighborhood or ball around the current parameters. So you move sort of in like the flattest direction in that ball. Instead of just optimizing for the parameters with the lowest loss, which tend to lead to much sharper minima on their own. So the other method that we experimented with is in this paper, which interestingly is sort of like a method that people have sort of actually used for many years in NLP, is stochastic weight averaging. So you're basically just like averaging your weights, like for example, throughout training, like according to how they sort of vary during stochastic gradient descent. This also works, but at least in our experiments, in terms of this, in this compression regime, it didn't work as well as sharpness aware minimization. Okay, so here are some results. These are very high level results. There's a lot of like averaging going on here. So on the left are our results for model pruning. And so these lines are averaged over all of the glue tasks. So this is like a benchmark that's measuring a suite of sort of like language understanding tasks. And so here we're taking like a BERT model and we're fine-tuning it on these different tasks, and then we're compressing those fine-tuned models. And we want to, so the gold star in this plot is like where we want to be. So that's like the highest accuracy and the highest sparsity, which is going to sort of correspond to the highest efficiency. It's a little hand wavy. If people are familiar with this area, I'm happy to take questions on more details later. So the green line represents sort of like the baseline accuracy of just like fully not compressed models. The blue line represents the performance of models that were fine-tuned using sharpness aware minimization. And then the orange line is just like fine-tuning using a regular sort of typical atom optimizer. And so you can basically see for a given sparsity level, the models that were originally trained using sharpness aware minimization just perform better pretty consistently. Yeah, at sort of any level of sparsity. So they're more prunable. So then on the right, this plot is kind of like a lot to look at. These are some results for model quantization. So again, the main takeaway here, so the SAM bars are the blue ones again, and the atom, the regular optimization bars are the orange ones. Basically the blue bars like tend to be higher than the orange bars, which again means that SAM trained models are more quantizable, as well as being more prunable than the sort of atom trained models. So it also seems to be helping there. Yeah, something that is the one other thing I'll point out here that's kind of cool, although I don't know how much detail I'm gonna have to go into to explain it, is this sort of purple line, QAT ref, as indicated in this plot. And you can see that it's like often higher than sort of both bars. Mostly look at the dark bars, not the light bars. And so that's actually like a really strong baseline using quantization aware training versus post-training quantization. So you can imagine if you know you want to quantize a model, you can train it not quantized, but like incorporate a quantization loss in order to learn parameters that are more quantizable. It's a similar idea to sort of what we're doing, except our approach is a little bit more general. It's not specific to quantization. And so I thought it's kind of interesting and kind of cool that actually our approach, it is a post-training quantization approach, but it performs like on par and sometimes better than actually a quantization aware training baseline. Yeah, and so we don't need to talk about this. This is like the breakdown across all of the glue tasks. It's not averaged. We can talk about this if you want in questions. And so because there's some evidence in the literature that flat models in flat minima are more generalizable than models in sharper minima, we were also kind of interested in looking at like broader definitions of success of a compressed model. So there's an increasing and very interesting body of work on really understanding the impact of compression and sort of like efficiency in general on model performance. So typically we're measuring sort of like top one accuracy, and we want to maintain that top one accuracy, as we make the model as efficient as possible. But it's sort of unclear what you might be losing. So there's some work showing that actually those models don't generalize as well, or they may be exhibiting increased biases that we don't necessarily want. And so here we're interested in seeing, we're looking at transfer basically. And sort of like, are these subnetworks that these like sort of pruned subnetworks that we're discovering, or like winning tickets in the sort of lottery ticket hypothesis literature that are being induced by the sharpness-aware minimization, are they transferring better? Are they sort of more generalizable, useful subnetworks of the model compared to the regular atom optimization across tasks? And so what both of these grids are showing is transfer, basically the improvement or decrease in performance of the SAM tickets versus the atom tickets but when using a pruned model that was pruned with respect to one task and then evaluating it on another task. So how generalizable are the pruned networks that result from sharpness-aware minimization versus regular optimization? And so in each of these cells is like a difference, and a positive difference means that the SAM model transferred better, and that's indicated in blue, and a negative difference means that the atom model transferred better, and that's indicated in orange. And sort of overall, blue seems, it's like SAM seems like it's transferring a bit better. And so I think that's interesting as well. Okay, I'm right about at time, but yeah, that's okay. I can be done. I'll leave up my last slide and maybe say like a couple words. So the one last thing that I don't have time to talk about this at all. But the one last thing that I wanted to say a couple words about are some potential applications of NLP to these sort of like bigger picture like issues with respect to the climate, and that is materials synthesis and materials decarbonization. Cement, steel, and petrochemical production together make up almost 1/4 of global emissions. And so if you can work on things that target reducing those emissions by making those processes more efficient, or making those processes require, for example, less like rare earth minerals, which are like required in efficient photovoltaics, for example, right now, powering solar energy. That's a really cool and exciting, and I think understudied sort of application of machine learning and data science. And I won't talk in detail. I've done some work in this space. I won't talk in detail about it now, but I'm happy to take questions or chat like offline by email or whatever. Yeah, okay. And that concludes my talk, and I'm happy to take questions. I want to leave time for questions.
Super, thank you so much. We do have a couple questions in Q&A, and we have time for maybe both of them. The first one from Evan is sort of a socio-technical question. What would be the best way to go about enforcing live accounting for models?
Hang on, I'm sort of reading
Yeah.
the question. Also, it has some more details. And I figured out the button. I'm finally getting good at Zoom after like 3 years. Enforcing live accounting. Yeah. So my first answer is that like, I feel like it shouldn't necessarily be about enforcing live accounting. I think that the biggest contributions to emissions of running models is like not from people who are downloading and running models off of Hugging Face. I think it's like models that are in deployment at a company, and they are like perfectly capable of measuring that. And I think they do. They're just not necessarily reporting the numbers. So maybe if something, so we just don't really know what they are. There do exist a number of packages that have been developed for measuring or estimating the carbon emissions due to your own machine learning model development and inference in them. One of the biggest challenges is actually getting like the estimated carbon emissions data. So getting the energy isn't that bad. Most hardware has like pretty good software estimates of the energy used. So the best thing you can do is like you get an energy meter and you plug the machine into that, and that plugs into the wall. But that's like really annoying. But the software estimates of that are quite good. They're usually off by like a constant factor, and you can kind of adjust for that. And then the hard part is actually translating that energy into carbon emissions. So unfortunately, like basically all of the tools that I know of cost money to get that information. The information is not freely available. So that's, I think, one blocker, like the biggest blocker to just like implementing something that's really easy to use and to make widespread. Should I move to the next question? Sorry, I've never done a webinar Q&A. Let's see. So it looks like Evan asked, do we know approximately the scaling between training energy use and inference use per inference? Like if we double the number of parameters, and so about double the training cost, is each inference also doubled in cost, or is it less than linear scaling? Yeah, that's a good question. Okay. So one thing I can tell you is, yeah, so training energy use. So basically, every time you look at an example during training, you have to run an inference, and then you also have to like compute the gradients and backpropagate the error. And so what that ends up being is about 3x. Like, so each step during training requires about 3 times the computation as just one inference step in order to compute like all the errors. That's one thing. The other, so that's not all of your question though. So the other part of your question is like, if we're increasing the number of parameters, so the thing that gets complicated is, so you're talking about increasing the number of parameters. You also need to think about like the number of examples you actually need to observe. So an interesting trade-off is that the larger the model, the faster it usually converges. And so you can actually look at fewer examples, even though the energy or like the computation required for each example is more. So yeah, so I think, I don't have the numbers off the top of my head, but I think the way that it works out is that basically you want to, like, training larger models is more efficient for a given budget, basically, if that makes sense.
We are at time.
Okay.
So I think I would encourage any folks that have additional questions to reach out to our speaker directly. And yeah, super. Thank you so much for joining us today, Emma. This has been a really wonderful and informing talk.
Yeah, thanks so much for having me.